can be done. It's just a matter of factoring and stuff. But there's an easier way now. See, because I can rewrite this as the integral of the sum n equals 0 to infinity of x times x to the 8th to the n power dx. See, because remember, x over 1 minus x to the 8th is equal to the sum cr to the n, where c is equal to x and r is equal to x to the 8th. So I'm just applying the geometric series, yeah? So I take my handy-dandy function and I flip it over here to a power series, like so. Clean it up. So this is actually what? X to the 8n plus 1. And the answer is a constant plus the sum, n equals 0 to infinity of 1 over 8n plus 2, x to the 8n plus 2. There you go. Done. So if you're thinking about your life and about all the time that you've invested in learning to do trig substitution and hyperbolic substitution and partial fractions and all that other stuff, you might start to have some doubts. Like, why didn't we just learn this, right? What's the downside of this? What kind of answer do you have? Well, your answer is in terms of a function you don't know, right? Your answer is in terms of this power series, which is useful, right? Because in terms of approximations, you can just keep taking as many of the terms as you want to get a more and more accurate function to model the integral you're interested in, right? So there's a clear path forward to approximating this function you don't know in terms of higher and higher order polynomials. But still, you know, that's why we don't teach this and just this, all right? We're interested in closed form expressions of elementary functions that, you know, the better part of, well, since we've been studying things since the Enlightenment or whatever, we've been talking about these functions, exponential, sine, cosine, all these things. I did have a student that was doing research with me who became, he became uninterested in finding exact solutions because he realized that he could just find a power series solution to the thing we're doing. And I was just like, so annoying. Like, yes, you can find a power series solution, but the fact that it's a solution does not suffice. Like, we like pretty. We want our solutions to be pretty, right? So anyway, so that's one thing. Let me show you another example. Can I erase? F of x equals the natural log of x plus 1. All right. df dx is 1 over 1 plus x. But that is a geometric series. Because I can see c equals to 1, and the radius is minus x, right? And so that cleans up a little bit. That's the sum. N equals 0 to infinity, minus 1 to the n, x to the n. You're like, well, what are we doing? Well, what I'm trying to do is show you how we can find the power series for the natural log of 1 plus x. You're like, well, you didn't find the power series for the natural log of 1 plus x. You found the power series for its derivative. That's true. So what can we do? Integrate. That's right. So f of x is a constant plus the integral of df dx. So some constant plus the integral of this guy, which is some constant plus the summation n equals 0 to infinity minus 1 to the n divided by n plus 1 x to the n plus 1. Now, is there an arbitrary constant in the formula for natural log? Well, no, there's not, right? So we need to address this issue. How do we pin down that constant? Let's see here. How about 0? 0 is a nice thing. F of 0 is the natural log of 0 plus 1, which is the natural log of 1, which is 0. And that's supposed to be equal to this constant, which we don't yet know, plus what? What is this series? Plug in n equals to 0, you get x. Plug in n equals to 1, you get minus 1/2 x squared plus 1/3 x cubed plus dot 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 dot. I wrote it out symbolically like this, but what are we doing? We're putting x equal to 0, right? So all of that is gone, right? It's all 0. So look, the constant is 0. So if I was a more irresponsible teacher, I could have pretended you didn't have to add a constant here, and I could have just got the right answer, and you wouldn't have known it. Until you tried to work a problem where you have to add a constant, which doesn't work out to 0, and then you would have been wrong. You know, but by then, I've already sold you on the slickness of this lecture, so my car salesman job would be done. But I do try to show you where the technical details are. So there it is. Anyway, so what do we got? We have the natural log of 1 plus x is in fact equal to the sum n equals 0 to infinity minus 1 to the n over n plus 1 times x to the n plus 1. Yeah.
What is x equals 0 there?
Oh, I'm plugging in x equal to 0.
Oh, okay.
Yeah. The whole blue line, I'm looking at what happens at 0 because that'll pin down what c is. That's all. Good question. So, hey, apparently we can do a lot more than just the straight up patterns of the form c over 1 minus r. If we can find a function that either integrates or differentiates to the pattern c over 1 minus r, that also we can find a power series for using this technique. There's a little bit more mileage to get out of this example before I leave it, though. How about the interval of convergence here? What's the interval of convergence? So the interval of convergence, we definitely know that minus 1 to 1, right? Minus 1 to 1 is a subset of the interval of convergence. How do I know that? We had r equals to minus x, right? So the absolute value of r equal to absolute value of x less than 1. So where I applied the geometric series result, right? Where I applied the geometric series result, the interval of convergence was minus 1 to 1. But notice that we don't know that the interval of convergence is the same for a function and its derivative. Differentiation and integration conceivably could change the interval of convergence. As a general rule of thumb, integration tends to add points, and differentiation tends to take away points. We're going to see that integration added a point in this example. So the interval of convergence for the derivative is straight up minus 1 to 1. Okay? Like this series has IOC minus 1 to 1. That's not in debate. But the IOC for the natural log, I need to give it a name here. I will call the series Bob. There we go. The IOC for Bob It doesn't have to be the same. Let's check the endpoints. What happens when we put x equals to 1? You get what? Sum n equals 0 to infinity minus 1 to the n divided by n plus 1, right? What happens when you put x equals to minus 1? What do you get? Sum n equals 0 to infinity. Minus 1 to the n times minus 1 to the n plus 1 over n plus 1. What is that one? So what happened? What happened? Well, the x equals minus 1, that's out. Because we're looking at what? Minus the p equals 1 series. This diverges. So it diverges by p equals 1. How about x equals to 1, though? What is this? This one keeps coming up today, right? This is the second time that the alternating harmonic series, right? That converges by the alternating series test. So then what? So you put this together, the IOC for Bob is actually equal to what? Minus 1 not included, 1 included. By the way, take a step back and look at what we have here. See this? This is the natural log of 1 plus 1 equals to that, which is the natural log of 2. I told you I couldn't derive it that day. This is why, because we needed this calculus to see it. So there you go. That's why the alternating harmonic series converges to the natural log of 2. Because it in fact is the power series for log of 1 plus x when x equals to 1. Which I think is kind of neat. Let me show you another one of these guys. So example 8. If we have f of x equals minus 1 over x plus 1 squared, then if we look at the integral of f of x dx, what's that equal to? I think it's 1 over x plus 1, right? Plus a constant, yeah? Which is the sum, n equals 0 to infinity of minus 1 to the n, times x to the n plus a constant. And then to find the power series for f, I differentiate my integral. This time, no need to fit a constant, right? Because the constant differentiates to 0. And here's the answer. Sum n equals 1 to infinity minus 1 to the n times x to the n minus 1. And there you go. That's the power series for minus 1 over x plus 1 squared. So this trick I did, it goes both ways, yeah? The first one I differentiated, found the geometric series, integrated to get back. This one, I integrate, apply the geometric series, differentiate to get back. What if I did this, guys? What if I had another example that would work something like this? What if you had this? What if you had 1 over 3 plus x to the 4th? What would you do? You could still play this game, right? Integrate once, it gets you to the x cubed. Integrate twice, x squared. Integrate 3 times, x in the denominator. Apply geometric series, and then differentiate once, twice, and the last time you're back where you started. So you can apply this trick, if you can find the function you're looking at to be equal to 1 over something of the form c over 1 minus r, after so many derivatives or so many integrals, then you can apply this trick and come back. So I have given you enough information to do a wide swath of your homework. There's a lot that what I've told you today will solve. All right? And so for that reason, and because half of you aren't going to be here anyway tomorrow, no class tomorrow. Is that okay? Yes. Oh, okay.